which contains metal and ligand in the same proportion as dictated by the stoichiometry of the complex, right? Suppose metal and ligand are present in the ratio of 1:3 in the complex, then that solution must be 'obviously asked how concentration of metal only, concentration of ligand only. Then we will subtract because we know the total concentration of each solution is same, and we know that. And you subtract the concentration of the ligand from the total concentration, you will get the concentration of the metal. So similarly, if you have mole fraction of the ligand plotted on the x-axis, we all know that sum of the mole fractions of different constituents in a solution is always equal to 1. So if the mole fraction of ligand comes out zero point 0.7, obviously the mole fraction of the ligand must be 0.3, because 0.7 plus 0.3 is equal to 1. So mole fraction of ligand is known. Mole fraction of metal will be 1 minus mole fraction of the ligand. So that is the standard procedure that we follow. You will understand things more easily when we go to the presentation. So let's go to the presentation. So this is stability constant we were discussing. This is the spectrophotometric determination, and we were discussing Jobs method. So Jobs method mole ratio, the metal ligand ratio is varied between 0 to 1 at constant total concentration. So concentration of the metal uh, is in one solution 0, and the concentration of the ligand is maximum. And then you slightly increase the concentration of the metal gradually, and decrease the concentration of the ligand also by same proportion, and you prepare a series of solution, and you record the absorbance of different solutions, and absorbance is plotted by same, as I said, mole fraction of the ligand, or mole fraction of the metal, or concentration of the metal, or concentration of the ligand. There are 4 different ways in which you can generate a graph. एक मिनट कोई ज्वाइन कर रहा है. Mehak Kaur is joining. Okay, Mehak, welcome. Mehak Kaur. ठीक है, तो आपके पास 4 ऑप्शंस हैं. एक्स एक्सिस पे आप क्या प्लॉट कर सकते हैं? आप कंसंट्रेशन ऑफ मेटल यूज कीजिए, कंसंट्रेशन ऑफ लिगेंड यूज कीजिए, या मोल फ्रैक्शन ऑफ लिगेंड यूज कीजिए, या मोल फ्रैक्शन ऑफ मेटल यूज कीजिए. सो देयर आर 4 ऑप्शंस अवेलेबल फॉर द parameter to be plotted on the x-axis. If only one complex is formed, so say the stable complex is only one, and having composition MLN, the absorbance is measured at lambda max, where neither M nor ligand absorbs, but only complex absorbs. Then N, the average number of ligands bounded to the metal, can be determined by where Chi is the X or chi is the mole fraction of the ligand divided by 1 minus chi. Yeah, this is mole fraction of the metal. What is max? Max means that particular mole fraction of the ligand at which absorbance is maximum. So on the y-axis you are plotting the absorbance, on the x-axis you are plotting the mole fraction of the ligand. So chi max is that particular mole fraction of the ligand at which the absorbance has maximum value. So very common method for determination of composition of complexes, equimolar mixture of metal, that I said yesterday, that our effort is always to make two solutions having same concentration, metal and ligand, and we then mix them in different proportion while keeping the total concentration same, or mix to give a series of solution having same total concentration of metal plus ligand but varying concentration of metal and ligand. Say, I gave an example that I prepare 10 raised power minus 2 molar solution of both metal and ligand, and then I prepared 10 to 12, 11 solutions, solutions in which in the first case I take metal 0, no metal is added, only ligand 10 milliliter ligand is added, and I prepare first solution. So this is pure ligand, and last one is pure metal, because in this tube there are 10 milliliters of the metal solution added, nothing is added from the ligand, so it is pure metal in the 10th tube. So these solutions should not absorb, pure metal and pure ligand should not absorb at this wave at the lambda max which we are using. So the complex that is formed during this process will have different color and different composition than the metal and ligand. So you need to know first the lambda max of the solution. So take any tube other than first and last, because first tube has pure metal, pure ligand, and last tube has pure metal. So take any other tube which is having both metal and ligand, it will have some proportion of the complex formed, and put it in the give it on the spectrophotometer and ask the spectrophotometer to scan this solution from 400 to 800 nanometer if it is colored in the visible region. So the spectrophotometer will plot a graph against the graph of the absorbance, but on the x-axis there will be wavelength or wave number or frequency. Any three of them will be plotted on the x-axis: wavelength, wave number, or frequency. So if it is wavelength in nanometer or angstrom, the maximum of the peak will provide you the answer about lambda max. So once you determine the lambda max, then fix the spectrophotometer on that particular lambda max and determine the absorbance of each of these solutions which have been prepared by changing the concentration of metal and ligand while keeping the total volume and total concentration constant. So in the second tube, you have 1 milliliter of the metal solution, 9 milliliter of the ligand solution. So concentration of metal plus ligand is 10 minus 2. 3 milliliter of the ligand metal and 7 milliliter of the ligand. Then you have fourth one, 4 milliliter of the metal, 6 milliliter of the ligand. Then you have fifth tube, equal volume of metal, equal volume of ligand. Then you have sixth tube, 6 milliliter of the metal and 4 milliliter of the ligand. Similarly, you go on and increasing the metal metal volume and decreasing the volume of the ligand solution, because you have to keep the total volume 10. In the last tube, you have 10 milliliter of the metal, 0 milliliter from the ligand. So concentration in all these cases is 10 raised power minus 2. So that's the key. The total concentration is known for each case. So if you plot that's why if you plot a graph between absorbance and the concentration, says concentration of the metal. If you know the concentration of the metal from the graph, you will know the concentration of the ligand by simply subtracting the concentration of the metal from 10 raised power minus 2, because concentration of this solution overall, this is concentration plus of metal plus concentration of ligand, that is known, that is 10 raised power minus 2 in all the cases. So if you know the total concentration, you know the concentration of the metal, you can find out the concentration of the ligand by subtracting the concentration of the ligand from the total concentration. Similarly, if you know the concentration of metal, you can do the reverse thing also, right? So this is an general equation, m plus n times L, depending upon what is the ratio between m and L is 1 is to n. N can have any value, 1, 2, 3, 4, 5, 6. So gives mln. So the equilibrium constant or the stability constant is given by mln concentration divided by free metal concentration into ligand concentration raised to the power n. A series of solutions are prepared whose concentration C metal plus a ligand is constant. So that is, say, 1 molar at 1. So first tube is, say, if you are to prepare the 1 molar solution of the ligand plus metal constant. So in the first solution, the metal concentration is 0.1, ligand concentration is 0.9. So itne molar and itne molar. So add, it becomes 1.01 molar. Similarly, in the second, 0.2 plus 0.8, 0.3 plus 0.7. These are different combinations by which you can generate different combinations of the solutions varying the concentration of the metal and ligand, but at the same time keeping the total concentration metal plus ligand constant, right? So ionic strength. So we want to make sure that the complexation process is not affected by the change in concentration of the metal concentration of the ions in the solution. So to keep that factor silent, we keep the you add the excess of potassium perchlorate, so that the ionic strength, the number of ions in the solution, do not differ significantly when you change the concentration of, when you decrease the concentration of metal and increase the concentration of the ligand. So any physical property can be, it's not necessary that Jobs method does not say that you always record the absorbance. Any physical property can be technically recorded, which changes with the concentration of the metal. So we take the advantage of the absorbance, because absorbance, according to Beer-Lambert law, is dependent on the concentration. So we presume that when the metal and ligand are in the right kind of ratio, right kind of proportion, the concentration of complex is maximum at that point in time. The tube in which the metal and the ligand are in proper ratio, that tube will have maximum concentration of the complex. And therefore, when you have maximum concentration of the complex, the absorbance will be highest, because Beer-Lambert law says that absorbance is directly proportional to the concentration of the absorbing species. So ideally or theoretically, it is not necessary that you record absorbance. Any physical property which changes with change in concentration of the complex ion can be used to determine to find out this the composition of the complex. So any physical concentration plus ligand, this is mole fraction of the metal. The sum of these two is equal to 1, right? So because mole fraction is varies, it cannot be more than 1, it cannot be less than 0, because 0 mole fraction means pure component. So it has to be more than 0 and less than 1. So if you know the mole fraction of the ligand, you can find out the mole fraction of metal by just subtracting that mole fraction of the ligand from 1. 1 minus, if you know, if there are two components in a mixture, A plus B, if you know the mole fraction of A, mole fraction of B will be 1 minus mole fraction of A. So that's as simple as that. A maximum in the curve, when the ratio of the concentration or mole fraction are in the same, are same as in the formula of the complex, it is at that point in time that you will observe the maximum in the absorption curve. So mathematically, we write the concentration of the complex is equal to the, from this equation, if you cross multiply this equilibrium constant equation, the concentration of the complex is equal to K into M into Ln. So M, what is the concentration of the free metal? Concentration of metal and ligand in each tube is same, and that we know. So what is concentration of the metal? It is C minus L. So if you know the concentration of the ligand, you can find out the concentration of the metal, or vice versa. If you know the concentration of metal, you can find out concentration of ligand by just subtracting the concentration of ligand from the total concentration that we know beforehand. Before doing experiment, we know what is total concentration. So this is same thing. Now MLN, the concentration of the complex is equal to K raised to power L raised to power n, and within the bracket in place of M we can write C minus L. So you open it, it becomes Kc L raised to power n minus K into L raised to power, this is L raised to power n, and here is n, one more L, so it is n plus 1. So you open this bracket, it becomes these two. Now this is how the graph will, you plot absorbance on the y-axis, you plot concentration of the ligand or concentration of the metal or the mole fraction of the ligand on the y-axis. This is how the graph will appear. There will be a position where the curve will have maximum value. You drop a perpendicular from that maximum value, you on the x-axis you will find out the concentration of the ligand if the concentration of the ligand has been plotted there. So once you know the concentration of ligand, you can find out concentration of metal, right? Or it can be mole fraction. So the change in the absorption curve with change in concentration, that is known as slope of the curve. The slope is very high here because the absorbance is changing with the change in concentration of the ligand. But at this point, which is the maximum point, which is the maximum absorbance, when the curve deflects or curve changes its course, it comes downward, the slope is said to be zero. The position at which the maximum of the curve appears, the slope of the curve is zero. Or in other words, slope is given by dA, change in absorbance with change in concentration of ligand. So that is zero there. So we write the change in concentration because absorbance is directly proportional to the concentration of the complex. So we write dmln by dl is equal to 0. I hope you understand this thing. For any curve which goes up first and then drops down, the position of the maximum mathematically can be represented by by a fact that the slope is zero at the maximum of the curve. The slope is given by dy by dx. Dy means what is plotted on the y-axis, and dx is what is plotted on the x-axis. We have plotted on the y-axis. We have plotted on the y-axis the absorbance. So technically we will write dA by dL, and we have plotted on the x-axis the concentration of the ligand. So I will write dA by dL is equal to 0. The change in the absorbance with the change in concentration of the ligand is 0 at the maximum. And then we know that the absorbance is directly proportional to the concentration of the absorbing species. So we write the dmln, the change in concentration of the complex with change in concentration of the ligand is 0 at the maximum point. And the mln, then we know that this is equal to this equation. So minus this is n into kc into L raised power n minus 1. If you differentiate this equation, n comes down, it becomes n kc and n minus 1 here, and n plus 1 here, k and L raised to power n, because it is n plus 1 minus n minus 1. So 1 and 1 go, and we are left with L raised to power. This is how differentiation is done. Dx by dx square by dx is 2x, because 2 comes down and x raised to power 2 minus 1. So we have done differentiation. Because this whole thing is 0, we can take one part on one side, another part on the other side. So it's n kc L
n minus 1, n plus 1, k this. So dividing by, taking the common things out, because k is common, so you can strike out k and k. Similarly, L raised power n is common, you can strike out n raised power. L raised power n minus 1 is common, so you strike out n minus 1 from here. Here will be left n, L, 1 L will be left here, because n minus 1 is 1 less than n. So 1 L is left here. So on the right side, left side, we are left with n and c, because k goes and L raised power n minus 1 also goes. On the right side, we have n plus 1 into L, k goes. So this is the relation that we get from, the between what is C now. C is total concentration of the metal plus concentration of the ligand. So N into M plus L give into N is equal to N plus 1 into L. So if you open up this becomes Nm, this becomes Nl, this becomes Nl again plus L. Nl and Nl goes, we are left with Nm is equal to L. So L is equal to Nm. N is equal to concentration of L and concentration. So you find out what is N. N is nothing but how many ligands are attached to the metal in a complex. If what is the formula of the complex can be determined by the N. If N is equal to 6, it is Ml6. If N is equal to 4, it is Ml4. If N is equal to 3, it is Ml3. So formula of the complex is, in fact, knowing in what ratio metal and ligand are present in the complex. So that was our aim. So from the graph, if you find out L, you can find out C. You can find out the concentration of the metal by subtracting the concentration of the ligand from C, total concentration. And you divide L by M, you get N. N is the stoichiometric ratio in which metal and ligand are present. This is how Jobs method operates. So experimentally, when you go to the lab, how will you do this experiment? You will take a metal salt, you will take a ligand, you will make prepare a solution of both of these, which are having same concentration. Then you will take 10 test tubes and mix these two solutions in such a way the total volume of all the total volume of the solution in all the 10 tubes is same. So you will add 0 and 10 milliliter in the first, 1 plus 9, 2 plus 8, 3 plus 7, like this. You make 10 solutions. Then you will see the change. You will see the if the complex is colored, then it will different tubes will have different intensity of the color. That tube which will have the highest intensity will have the probably the metal and ligand in the proper proportion, the exact proportion. You take any of these tubes which has color, you take that tube and place a portion of that solution in the spectrophotometer and ask the spectrophotometer to scan that tube from 400 to 800 nanometer, and you find out plot a graph. The instrument will plot itself a graph between absorbance and the wavelength, and that the maximum position on the y-axis, you find out corresponding wavelength on the x-axis. So that will tell you what is the lambda max. Then you fix the instrument. You give command to the instrument to fix the wavelength now at this particular wavelength, and you take one by one all the 10 solutions and place them in the spectrophotometer and record the absorbance. And then you plot a graph between concentration of ligand, say, or the metal, that's your choice, versus absorbance. The maximum of the curve, if the curve bends downwards, goes up first and then bends downwards gradually, there's a curve which is a rounded shape, then it indicates that there is equilibrium between left side and the right side. On the other hand, if there is sharp rise and then sharp decline, then that means the reaction is complete. There's no equilibrium. The complexation has gone on the right side, complete extent. Then you can find out the composition of the complex by finding out the ratio of the ligand by ratio of the concentration of the ligand and concentration of the metal on the denominator. So n will always have value greater than or equal to 1. If the one ligand binds to the one metal, the n is equal to 1. If there is two ligands binding to the metal ion per metal ion, it is Ml2 type situation, then n is having equal to value equal to 2. The three ligands binding to one metal ion and will have the value 3. So ligand concentration will be 3 times than the metal concentration in that situation. So accordingly, you can find out the concentration. Now let's see how mole fraction is used. Now, if you use talk in terms of the mole fraction and not in terms of this concentration, now then how does the Jobs method operate? Cry is the mole fraction. And what is mole fraction? It is the concentration of the ligand divided by concentration of the ligand plus concentration of the metal, or total concentration in the denominator and concentration of the ligand in the numerator. So max stands for that query solution at which the absorbance is maximum. So mole fraction of the cry stands for mole fraction of L, and 1 minus cry stands for mole fraction of the metal. Because as I said earlier, the sum of mole fractions of the metal and ligand is always equal to 1. So what is concentration of the metal here? It is the Cm, the concentration that we had added initially. This is concentration of free metal in the equilibrium situation. That is free metal ion concentration minus concentration of the complex, because some of the complex or most of the metal has been complexed, small amount of it may be free, so that is M. So it is total concentration minus the metal which has been complexed. So metal can be also written as 1 minus cry into N. Cry is a number. It is just a ratio. So it has to be multiplied by the N. N is the total concentration. So to get the concentration, so 1 minus cry into N, M into Ln. Similarly, concentration of the ligand is equal to Cl. What is the total concentration that you added at the start of the solution minus N mln, N times, because the ligand, it is one metal ion binds N ligands, so N times mln. So concentration of the ligand initially was cry into N minus N mln. Again, we'll use the same formula, same principle, that the concentration, the change in concentration of the complex with respect to change in concentration of the ligand, or change in concentration of the change in the with respect to the concentration, not concentration here, the mole fraction remains zero. At the top of the curve, the concentration, the slope is zero. So change in concentration of the complex with the mole fraction of the ligand is zero. That's now the new terminology when you are plotting on the x-axis the mole fraction of the ligand rather than now concentration. So the change in concentration of the metal divided by this, here is metal. So you differentiate this solution with respect to the cry. So this is, when you open it, it is N minus cry N. So the differentiation of the N is 0, differentiation of cry N is N, and differentiation of this whole thing is 0. Similarly, you take differentiation of L, dl by d cry, this is 0, not 0, this becomes N, because cry becomes differentiation of the cry with respect to cry is 1. So this is N, and this becomes 0. So these are the equations that we develop. D mln by d cry is 0, because by definition that is 0. Dm by d cry from this equation is minus N, and dl by d cry is N, total number of moles. So dm by, again written in the same equations written again. So now you expand this equation. When you have two parameters and you are differentiating with respect to cry, you will differentiate them one by one. So first M will be taken out, and d cry L raised power N by d cry, and second time plus, this is the rule, these are rules of the differentiation, L raised power N dm by d cry is equal to 0. So then you take the differentiation of this, N will be coming down, M L raised power n minus 1 dl by dx, d cry, or dx plus n ln as such dm by dx is equal to 0. Then nm, it remains same, L raised power n minus 1, and dl by dx, we have just written it equal to n, we'll place it n, plus L raised power n minus dm by dx, we have just written it minus n equal to 0. Then take n common, so inside bracket we will have n L raised n m raised L raised power n minus 1 minus n taken common, L raised power n is equal to 0. So because n cannot be 0, this must be 0, this bracket must be 0. So or you take this outside, this side, transport it this side. So n and n in any case will go. We're left with n m L raised power n minus 1 L raised power n. Again, will be left with nm equal to L. This is same thing that we got in terms of the concentration also. The value of L is given by the ratio of the concentration of L and concentration of the M. Right. So nm is equal to L. This is what just we got. But M can be written as 1 minus cry into N, and L minus mln. This is what we were written initially as concentration of the M. Similarly, concentration of the L can be written cry N into minus here cry N minus N mln. So you again equate these, open these equations. This term and this term on different sides get cancelled out, and then we are left with nm 1 minus cry. On the right side we are left with cry n. So n and n goes, big N, small n is equal to cry by 1 minus cry, where cry is the mole fraction of the ligand and 1 minus cry is mole fraction of the metal. So same thing we arrive at, we have derived this situation. Now, if the maximum of the absorption curve occurs at the 0.5, this is the equation. This is not mole fraction. This is concentration of the ligand. It's wrong here. It's not mole fraction of metal ion. It is, say, concentration of the metal or ligand. So it is 0 because mole fraction cannot be 0. Mole fraction has value greater than 0 and less than 1. So, and mole fraction cannot be more than 1. So it is 1.2 means it is concentration. So the maximum of the curve is happening at 0.5. So the total, so the complex is 1:1. So if the total concentration is 1 mole, so the 0.5 is the concentration of the ligand or metal. The concentration of the ligand is 1 minus 0.5. That becomes, so it's 1:1 complex. Iron and thiocyanate case, this is the situation that you get maximum when you have concentration of the metal or ligand at the center, right? So when you have 1:2, then you get the curve like this. The ligand has ligand concentration bit higher. It is not 0.5, it's bit higher, 0.67. This is what 0.67 in the case of 1:2. It is 0.67. The mole fraction of the ligand is 0.67. Mole fraction of metal is 0.333. And in the case of 1:3, the mole fraction of the ligand is 0.75. Right? So this is 1:2, and then 1:3, the mole fraction is 0.75, right? Or the concentration is 0.75 of the ligand, and the metal is 1/3, 0.25 of the concentration of the metal ion. So in this way, you can find out the the equilibrium constant. And once you know the metal concentration and the metal and ligand concentration, and you also know the concentration of the complex, then you can obviously find out the equilibrium constant also, because the concentration of the complex is given by the mole absorbance divided by molar extension coefficient into L. And if you know the molar extension coefficient and you know the absorbance, you can find out the concentration of the complex, and you know the concentration of ligand and metal. Therefore, you can easily find out what is the equilibrium constant of a complex. So that is all about Jobs method and equilibrium constant or stability constant, how it can be determined if situation allows. Uh, mm, Inshallah, we will do this experiment in the lab, and you will have a better understanding how things operate in different situations. So iron thiocyanate is generally taken as a test case because the complex is formed easily without heating, without refluxing. You just add two solutions, it becomes blood red color. Iron 3 and thiocyanate 1 negative, they form complex in 1:1 stoichiometric ratio, and you can easily decipher that ratio by following the change in absorbance with change in relative proportion of the metal and ligand in a series of solutions where they primarily total keep the total concentration constant but change the relative concentration of metal and ligand. That is all about the second unit. This was a relatively smaller unit, and we have finished it in time. If you have any questions, I'm here